my name is Graham Junsar, and this is my video lab report for Lab4 circuits. The goal of this lab is to predict the behavior of circuits containing different electrical components and then check our predictions by measuring current and potential differences along the circuit. The models and fundamental physical principles used in this lab are the loop rule and current conservation rule, which are Kirchhoff's laws, and the formulas for change in electrical potential across different circuit components. For our preview of results, the current in the 2-resistor circuit was theoretically 0.02 amps, and we measured it at 0.01 amps, and the RC in the second circuit was calculated to be 3.7636 seconds. So on this left image, we see the change in voltage across a capacitor, change in voltage across a battery, and a change in voltage across a resistor. In the middle, this is the loop rule, which is the sum of voltage differences across a loop always equals 0. And on the right is the junction rule, which is the sum of currents essentially going into a junction is equal to the sum of the currents going out of a junction. System in each of the two circuits would be the ammeters and voltmeters, which measure the current and potential difference at or along some points in the circuit respectively. And then the surroundings would be the circuit itself, which includes the wires and electrical components, along with the actual electrons moving in the wires creating the current. We were asked to predict the current in the circuit at the two locations indicated, and we know that because there are no junctions in the circuit, the current should be the same everywhere because of the junction rule. And also that when the ammeter is reversed, the sign of the reading should be reversed because the current is going in the opposite direction. So using the Kirchhoff's current law, we sum all the voltage differences to 0, and we are able to solve for I at 0.0204 amps, which is very close to our 0.01 reading we got from the actual circuit. When we measured the potential differences across the circuit as described in this diagram, here were the values we got. We gained 3 volts across the batteries, we lost 0.96 volts across the 47 ohm resistor, and lost negative 2.04 volts across the 100 ohm resistor, and the rest was 0. And our findings do confirm the loop rule as the sum of the voltage differences added to 0. And here I extended the graph that was provided to us in the instructions. To calculate the current reading from this ammeter if the circuit was switched to where the ammeter and 100 ohm resistor were in parallel, and we do this using Kirchhoff's laws for the change in voltage summing to 0. So the battery, the initial resistor, and then these two resistors in parallel is this equation, which actually goes to 0 for the negligible resistance of the battery. So finally, we calculated the resistance to be 0.0638 amps. And separately, for the original circuit, we calculated back from our measured voltage differences the resistances of these different components, and we noticed that they're slightly different from what they should be, and this is because the value for the amperage we observed from measuring the circuit is rounded from the true theoretical value. So it explains why these calculated resistances are different from theoretical. That's a possible source of error. For this circuit, we were asked to measure the time it takes for the capacitor to charge, and then calculate the time constant of the circuit, which is the time at which the voltage difference has dropped to 1 over E of its original value. And here's an example circuit that we made, and we noted that with a 10 ohm bulb in the circuit, the capacitor took 15.3 seconds to charge and 15 seconds to discharge. We want to calculate RC, and this is the circuit we use to calculate it. If we have a circuit with a fully charged 0.2 farad capacitor and a 20 ohm bulb, what would be the RC of the circuit? To find this out, we first look at the initial potential difference across the battery, across the capacitor at full charge is 9 volts, as we charge it with a 9 volt battery. So that means delta V0 equals 9. And we use this formula, which was given to us for the change in potential across a capacitor at a specific time. And we can use natural logs to solve for RC. And we noted that after 1 second, we measured the potential differences across the capacitor to be 6.9 volts. And using these two values, we can solve for RC like this. So we know what the delta V is at 1 second. So we plug in T equals 1. And through solving it, we get RC as 3.7636 seconds. So what if we were doing this lab in a simulation and used an ideal ammeter instead of an actual ammeter? In real life, all electrical components have resistance, so our assumption that the ammeters have no resistance in our calculations is incorrect, which may have thrown off our measurements. So with an ideal ammeter, one can assume that we have 0 resistance in the circuits, and this would lead to more accurate theoretical results. We're instructed to use an ammeter to measure how long it takes to charge the capacitor when connected directly to the battery, and we want to discuss why this measured time is different from the predicted time. This is because the measured time to charge the capacitor may differ from the predicted time because in real life, the capacitor might not be fully discharged or it may have some residual current, or because we have not taken into account the resistance of the wires or the ammeter in the circuit.